The second lecture of section 1.3 is going to start to focus more on how you might prove claims regarding the soup of a set. So just a reminder of the definition of the supremum of A, which, remember, supremum is another word for least upper bound. The first thing is, if you're going to be the least upper bound, you better be an upper bound for A. So that means sup A is greater than or equal to all elements in the set. And then if B is an upper bound for A, it has to be greater than or equal to the sup. This is just asserting that sup A is the least upper bound. And here I've drawn a picture. If you have your set A and it's bounded above, so that's like saying it's bounded on the right-hand side, it doesn't go all the way to infinity, then the sup is going to be right up against the edge of the set A, and then any other B that you select will be somewhere to the right of sup A. So something to think about, this definition actually gives us a way to answer the following two questions. So question one says, how could you prove that a given real number x is such that x is greater than or equal to sup A? And the second question is, how could you show that a real number x is less than sup A? So I recommend pausing the video before you take a look at my solution. So if you take a look at part 2 of the definition of sup, it says that if you know a number is an upper bound for A, then it's automatically greater than or equal to sup A. That tells me that if I want to show a number is greater than or equal to sup A, and I could apply the part 2 of the definition and say, I want to show that x is an upper bound for A. In other words, remember what that means. If I pick any element in my set, that element is going to have to be less than or equal to x. The moment x is an upper bound, you can apply the definition part 2. to infer that it has to be greater than or equal to sup. So then alternatively, if you wanted to show that x was less than the supremum, you could show that x is not an upper bound, because if x were an upper bound, then I would have found an upper bound smaller than the least upper bound, and that contradicts sup A being least. So here we could say show x is not an upper bound for A. And as I said, otherwise, sup A is not the least upper bound. And that's a contradiction. So sometimes when you want to prove that a number is the supremum of a set, you'll use the definition. You'll have to show that the number satisfies being an upper bound and that it's smaller than any other upper bound that you select. But there's also another way that the book introduces. It's called a lemma, lemma 1.3.8. When you hear the word lemma, you should think this is a theorem that is used to prove something else that's arguably more notable. So in this case, the lemma is how it's help for proving that a number is a supremum. So one thing I'll highlight here is you start off and you have to have already discovered that the number S you're working with is an upper bound for your set. So that means you have already satisfied part 1 of the sup A definition. So if you're going to use this lemma, you have to make sure you prove that you first have an upper bound. Then the second part, this is an if and only if statement, so it's an equivalent way of saying that S is the supremum of A. And this statement here that I'm going to highlight in red is an alternative way to show part 2 of the definition. So this is essentially going to give you a replacement. Instead of showing part 2, you're going to show this mixed quantified statement. Now, looking at that mixed quantified statement, I don't know about you, but it looks like a whole lot of symbols. We've got mixed quantification, which makes it trickier to parse. What exactly does this mean? So what I would like for you to do is try to pause the video and go through and see if you can come up with a high-level explanation of what this is saying. I suggest drawing yourself a picture to make sense of this. As much as possible, whenever you have this mathematical notation, it's really important to get some geometric context on what this is saying, and so that it has more meaning to you rather than just something you're memorizing. So here we have a number line, and we're going to assume that we're dealing with a set that's bounded above, because that's the only situation in which we're looking for a supremum. If you don't have any upper bounds, then certainly you don't have a least upper bound. So suppose my set A is something like this, and A lives to the left of where I've made this right wall. Then what this is saying is, if I have my soup, which I'm trying to say is S, and I subtract an epsilon off of it, so I make it just a little bit smaller, then I'm supposed to be able to find some little number A in here. It could be that A is S itself in the event that S is in the set. So here I'm supposed to get that there exists a little a in A that's larger than S minus epsilon. So if we go ahead and we look at this quantified statement, here when you see epsilon, I want you to think of a small positive distance. This is kind of like error. And we're saying that if you try to make S minus epsilon even a little bit smaller, you're going to find an element in the set that's bigger than it. So if you subtract even the smallest amount from S, S minus epsilon is no longer an upper bound for A, is what we're saying. So in other words, this quantified statement, so we're saying given a small change in the size of your number, I'm going to be able to find a little a bigger than my number S minus epsilon. That is how you prove, this is saying that S minus epsilon is not an upper bound. That is exactly this quantified statement, and we're asserting this for any distance, any small distance that we remove from S. Now it is possible, I said this, that the number A you get is S itself. I'll give you an example of when that happens. Suppose I have the set of just the number 1. If I take a look at this on a number line, all I have is the number 1 right here in my set. If I wanted to subtract epsilon off of that, I would get a new number to the left. Here would be 1 minus epsilon. And if I'm supposed to say, looking at this set A equals 1, the soup of that set is 1. It's the maxed element of the set. There's only one element, and it's the largest. So that's naturally the supremum. Now, since it is the supremum, it's going to have to meet the conditions of the lemma, which says whenever you make one even a little bit smaller, you should be able to find a little a that's bigger than it. Well, remember what little a is. Little a is supposed to be an element in your set. You only have one element in your set, so there's only one candidate for this. So here, a equals 1, which is also the sup of the set. And this is no matter which epsilon you pick. So sometimes you'll turn up a little a in the gap between s and s minus epsilon, and other times the sup, if the sup's in the set, the little a that you're returning might be the supremum itself. We can also adapt lemma 1.3.8 for infimums instead. This is true if we focus on the left side of the set rather than the right side. And so what I would encourage you to do is pause the video and see if you can come up with an analogous statement for infimums. And in this case, I want you to use I as the number that you're saying is the inf. So I'll start the lemma, and then you may want to pause from there and try and fill in the rest. So remember, infimums, these are the greatest lower bounds. I'm talking about the number that is right on the left side of my set. So again, you need to start with the assumption that you're dealing with a lower bound. So let I and R be a lower bound for A. So I want you to come up with what goes after the if and only if part. So I'm going to say then I equals inf A, if and only if what? You could draw yourself a picture to help figure it out. You've got I, and this is supposed to be the greatest lower bound, so that means that A is supposed to live here to the right and I is directly on the edge. What we're saying is that if you make I any bigger, it should lose the property of being a lower bound for the set. Because we're saying any number bigger than I is not a lower bound, since I is the greatest lower bound. So this is not a lower bound. So filling in what we should have here is for all epsilon greater than 0, there should be some little a in your set that proves that I plus epsilon is not a lower bound. And the way you do that, if it's not a lower bound, it means there has to be a number in the set that's even smaller than it. So the high level of what this box is saying is that I plus epsilon is not a lower bound for A. Now we're going to talk about how you actually prove lemma 1.3.8. So here's the statement again. It's an if and only if statement, which means we need to prove two implications. And we have a global assumption to the if and only if statement that S is an upper bound. So we get to assume that, and then we have to prove both directions. We need to show that if S equals the sup A, then that quantified statement holds, and also that if that quantified statement holds, S is the sup. Now there are different ways that you can do this. Let's say we're focusing on the forward direction first. So let me write out what we're trying to prove. So we want to prove that if S equals the sup of A, then for all epsilon greater than 0, there exists a little a in A such that S minus epsilon is less than A. Again, this is saying that S minus epsilon is not an upper bound. So using the high-level interpretation of what we want to show should give us a little bit more direction in what we're trying to do. We can prove this implication however we want, using any proof technique that we want. So we could prove it directly, we could prove it by contradiction, we could prove it by contrapositive. Some people might be naturally drawn to doing contradiction or contrapositive, and the reason why that is, well, one, people just like those proof techniques, but two, notice that right now I'm going to be assuming that if I were to do it direct, I'd be assuming S is the sup, and then I have to prove a for all statement. And proving a for all statement requires a more general argument. When I negate this highlighted statement, then I would get that there exists an epsilon, and so I'm working with just one number, and some people might find that easier to do. I'm going to prove this claim directly though. And let's just think high level for a moment what we're trying to do. We're saying we know that S is an upper bound and that it's the supremum. So that means when we say this part right here, we know that means that S satisfies the definition of sup A. And we want to show high level that S minus epsilon is not an upper bound. So if I want to show that S minus epsilon is not an upper bound, I need to go back up to my definition of a supremum, which is up here, and all I have to work with is part 1 and part 2. So we want to think about how the definition of sup A is going to allow us to argue that S minus epsilon is not an upper bound for our set. So take a moment and pause and think through this. So then why can't S minus epsilon be an upper bound for A? Well, S minus epsilon is less than S. Oops. I'm just going to say S here. S minus epsilon is less than S, right? Because we're taking epsilon, which is a positive number, and we're making it a little bit smaller. If S minus epsilon was an upper bound, we would have a contradiction to part 2 of the definition of sup A. So once we know it can't be an upper bound, then we can just use the definition of not being an upper bound to assert that there exists a little a. Now notice we're proving an existence statement. There are 2 types of existence statements that you should have learned from your proofs class. The first is constructive, where you actually say, if you have there exists an X, and you say let X equals. So you actually find it, you plug it in, you show it does what it's supposed to do. There's also a non-constructive proof where you go and you try to show that some other property that you know is true demonstrates or allows you to assert the existence of an element. And here we're using the part 2 of the definition to get to this place where an A has to exist. So we're not going to be saying let A equal something. We're going to be showing a series of logical steps that demonstrate that this number has to exist. All right, so I'm going to write up the proof. So in this direction, I'm doing this directly, so I'm going to assume that S is the supremum of A. Now, I need to prove for an arbitrary epsilon that I can get this A back, which means if I'm proving a for all statement, I need to introduce an arbitrary epsilon. So let epsilon greater than 0 be arbitrary. I don't care whether or not you say the be arbitrary part, you could just say let epsilon be greater than 0. Then, remember what that means. S minus epsilon has to be less than S. Because S is the least upper bound for A, S minus epsilon cannot be an upper bound for A. Since it's smaller than S, that would contradict this assertion that S is least. So by definition of upper bound, there must exist a little a in A such that S minus epsilon is less than A. This is really, we're saying the negation of the definition. And that's exactly what we wanted to prove. So we're done. So now we need to prove the backwards direction of the implication, and that's if for all epsilon there exists an A such that S minus epsilon is less than A, then S equals sup A. But we're going to do this, we could do it directly if we wanted. I'm going to do it by contrapositive just as a review of another way to think. So remember how a contrapositive of an implication works. When you have P, like if P then Q, the contrapositive is if not Q then P. So here I've negated, I have S, if S is not equal to sup A, then I have the negation of this mixed quantified statement. Now make sure that you're negating both quantifiers. It should be there exists such that for all A. And whenever you're proving an implication, you want to be focused on the conclusion of the implication and make sure you understand what you're trying to show before you start thinking about how your hypotheses are relevant. So when you look at this conclusion, it looks like a bunch of mixed quantifiers. What I would encourage you to do is try to understand what this is saying at a high level. Can you come up with just a way to talk about this in English using terminology that we've introduced? So I would pause and think about what that says, and then come back. So remember, epsilon was playing the role of a small distance that we were subtracting from S to make S a little bit smaller. So if we're saying there is an epsilon greater than 0, it's like saying, well, we're able to make S a little bit smaller. And then what ends up happening is, even though S minus epsilon is a smaller number than S, it ends up being an upper bound for our set. The high level here is for some epsilon, S minus epsilon is an upper bound for A. That's what we're trying to show. Now, go back to what we get to assume. We're assuming S is not sup A. That means that S does not satisfy the definition of the supremum. But one of our global assumptions of the lemma was that S is an upper bound. So if it's the upper bound but not the supremum, then that's got to be because it's not the least upper bound. There has to be some other upper bound for the set that is smaller. I'm going to write that out. And then we'll check back in. So we're doing the proof of the backwards direction, and this is by contrapositive, which I abbreviate CP. So remember what we get to assume. We're assuming globally, we know outside of the if and only if statement that we're looking to prove, we know S is given to be an upper bound. So I'm going to assume that S in R is an upper bound for A, but S does not equal sup A. What that means is that S is not the least upper bound. So by the definition, of sup A, there must exist some B in R such that B is an upper bound for A, but B is a number smaller than S. This is our way of saying S is not least. So if I draw a picture of what that looks like, we have our number S right here, and we're told that that is not the least upper bound of our set, which means it's not right up against the edge of the set A. There has to be some other B in here that is an upper bound that's even smaller. Now B could be the supremum, or it could just be another upper bound. I'm not asserting that B is the sup here. I'm just saying there has to be a smaller upper bound if S is not the supremum. So notice this picture kind of looks a little bit similar. And what we have is that B is playing, this picture looks just like the lemma picture we had before. It looks like B is playing the role of S minus epsilon. And then we have to ask the question, well, what's epsilon? Epsilon is that distance that you've subtracted off of S to make it smaller. So here's our picture. And remember what we're trying to do in our conclusion. In our conclusion, we need to assert that there exists an epsilon such that S minus epsilon is essentially an upper bound for A. Well, in this case, I need to introduce a value of epsilon and show for that value of epsilon that S minus epsilon is an upper bound. Well, we just said B is going to be playing the role of S minus epsilon, so really what we're asking here is what's epsilon? We're at the existence part, so we should be saying let epsilon equal something. Well, epsilon equals S minus B. It's just the distance between S and B. And we can note here the number we've selected is bigger than 0 because remember we assumed here that B was less than S because we said S wasn't least. Since B is an upper bound for A, we must get that for all A and A, B or A is less than or equal to B. That's the definition of an upper bound. But in particular, we're trying to say that S minus epsilon is the one that's less than or equal, that's greater than or equal to A. So if I look at what S minus epsilon is, we've cleverly chosen epsilon so that when I subtract what it is, B pops out. So I'm doing S minus our value that we selected for epsilon, S minus B. When I simplify that, I get B. And then I'm just borrowing what I already wrote on the previous line. B is greater than or equal to A. Well, let's look at what we were trying to do. We were trying to prove that there exists an epsilon, which we've asserted right here. There exists our epsilon. We made sure that it was greater than 0. Then we had to say that for all A and A, S minus epsilon was greater than or equal to A, which we've done. That tells me that this proof is complete. Now, if I was proving the lemma altogether at once, I would want to write the proof of the forward direction and the backward direction all together in the same proof. But for the purpose of teaching, I'm showing these separately. So that is it for this lemma. Make sure you're thinking about it at a high level, where you're thinking about what what the role of epsilon is, and that quantified statement is talking about a number smaller than s being an upper bound. I'm going to post some examples for you to work on, and I'll post the solutions to those examples. I recommend that when you work on the examples, you actually meet up with some of your friends from class, and have a Zoom session with them. If you need help getting in touch with classmates, let me know.